In this video, we are going to look at DC circuits, Kirchhoff's laws, as well as resistors in series and resistors in parallel. Kirchhoff's laws can be used to work out the current in any branch of a circuit, given the EMFs and resistances in the circuit. Kirchhoff's first law. This is a statement of the conservation of charge. It means that the total charge flowing into a junction in a given time is equal to the total charge leaving the junction in the same time. There is no charge build-up at a junction. In other words, the total current into a junction is equal to the total current out of a junction. The example is the network of currents shown there. The junction is this one. These are currents entering the junction, the two. So 4 plus 1, that's 5 amps, should equal the currents that are leaving the junction, which is 2 plus 3. 5 amps. So algebraic sum of the currents is 0. In other words, if you say I1 plus I2 plus I3 plus I4, you should get 0. There is no current right at the junction there. So currents in are assigned positive values, currents out are assigned negative values. Hence the difference there in the calculation in that manner. Now, the Kirchhoff's second law is a statement of conservation of energy. Each coulomb of charge gains electrical energy as it moves through the source of EMF and loses it as it moves through a PD. In one loop, the energy gained equals the energy lost. That is, the sum of the EMFs around a loop in a circuit is equal to the sum of the potential drops around the circuit. So when you talk of EMFs, look at sources of power. So that's this one. We have got this one. If you have a positive and a negative, then a positive follows. You add up the two, so it will be E1 plus E2. But if positive is followed by another positive, then the effect is you subtract the two EMFs. It has to be positive, negative, then positive, negative in order to add up the two EMFs. Right, so let's look at this one. The positive of this one is going to the positive of that, so which means it's going to be E1 minus E2. So that's what we have here. And then this is equal to the potential drop, so there's going to be a potential drop here, a potential drop there, a potential drop there as well. Now, the potential drops here are governed by this current I1. So it's going to be I1 R1 plus I1 R2. And then we do have I2 R3. So I2 R3 is traversing in the opposite direction as I1. So which means it's going to be subtracted from there. So I1 R1 plus I1 R2. This is supposed to be I1. Because this is coming from there. So I1 R2 should equal I2 R3. Or if you subtract I2 R3 should equal this algebraic sum of the EMFs. When using the law, each device must be traversed in the same sense in the loop, clockwise or anti-clockwise. So since we are traversing in the clockwise direction, that is from E1 and then back again to positive of E1, back again to negative of E1, we're going to say E1 minus E2. So it's going to equal these currents that are going the same direction clockwise, I1 R1, I1 R2 minus I2 R3. So please don't be confused by this. This is supposed to be I1. Now let's look at the example that is given here. Calculate the currents I1, I2, and I3. Now again, we look at Kirchhoff's first law first. That is, it concerns current. So we have a junction here. So that's the junction that we have here. And we do have I1 there, I2, and I3. Now we've been given the direction of motion of the current. So I1 is into the junction. I2 and I3 are away from the junction. So I1 should equal I2 plus I3. So which means you're making I2 the subject of the formula. It's going to equal I1 minus I3. Now considering loop AEDBA, AEDBA, so the outside one. It has only one power source. So it's going to be algebraic sum of EMFs equals the potential drop. So this 24 volts is equal to I1, as you can see. So this we're going to get 4I3 in the same direction plus 2I1. So 4I3 here and 2I1. So this is equal to that in that loop here. Now if you consider loop FEDC, there's this one. This one has one power source again. So it's going to be the algebraic sum of EMFs, we only have 27. So it's going to be 27. Now as you can see, I2 is going in the opposite direction as I3. So we're going to have, you could have minus 4I3 plus 6I2 if you want. Or you can have 4I3 minus 6I2. You could have all that. So 4I3 minus 6I2. Since we are traversing in the clockwise direction in the first loop, remember the first loop that we considered here, it was going 2I1 plus 4I3. We are going in the anti-clockwise sense. So this is anti-clockwise. So we continue to traverse in the same direction here so that we are consistent with what we did in the first loop. So it's going to be 4I3 minus 6I2 because I2 is going in the opposite direction of our traversing. You could also consider this loop if you want. That is the one that has got two EMFs. So it's going to be 24 volts minus 27 volts in that direction there. It's going to be 24 minus 27 is equal to 2I1 plus 6I2. So it's still the same thing. I think that should be easy to you. Now, since we have formed a system of simultaneous equations, we have 24 is equal to 4I3 plus 2I1, and then we have 27 is equal to 4I3 minus 6I2. You solve the two simultaneous equations, and then you're going to come up with the answer. Now, in this case, they chose to substitute for I2, which was I1 minus I3, and then put it in there so that we have the same for you to solve the simultaneous equation. Therefore, you get I3 as 4.5 amps and I1 is 3 amps. And then you go back to Kirchhoff's first law and substitute for the unknown that you haven't dealt with. So if you do that, you then get I2 is equal to minus 1.5 A. Now, where you get a negative sign there, it means that you have traversed in the opposite direction to the actual direction of that current. So it shows that I2 is flowing in the opposite direction to that shown in the diagram. Okay, let's just go back there in the diagram. So we thought I2 is going down like this, when in actual fact I2 is going up. Please let me know in the comments if you need further clarification on Kirchhoff's first law and second law. Now I'm going to apply Kirchhoff's laws to resistors in series and resistors in parallel. Now if you have resistors or a network of resistors in series, R1, R2 and R3, by Kirchhoff's first law, the current through each resistor is the same. There is no junction here. So we only have one path of flow of current. Then by Kirchhoff's second law, the PD across all three resistors is the sum of the PD across each one. So V is equal to the total voltage, that is V is equal to V1 plus V2 plus V3. Now dividing by I, since I is common for the three resistors, V over I is equal to V1 over I plus V2 over I plus V3 over I. And the total resistance of the network of resistors is equal to V over I, which is this one. So this becomes R1 plus R2 plus R3. So resistors in series, in order for you to get the sum or the total resistance, you simply add the resistances of the resistors. Considering resistors in parallel, by Kirchhoff's first law, I is this one, current entering the junction is equal to the currents leaving. So all the three currents are leaving, which should equal this total current that is entering in. So I is equal to I1 plus I2 plus I3. Then by Kirchhoff's second law, the PD across all three resistors is the same because each coulomb of charge delivers the same amount of energy to each resistor, whatever route the charge takes. So I1 is equal to V over R1 because the same V. I2 equals V over R2. I3 equals V over R3. And we know I is equal to V over the total resistance, where R is the total resistance, correct? So V over R, we can write it as V over R is equal to V over R1 plus V over R2 plus V over R3. Then we divide by V both sides. You get 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So for two resistors that are connected in parallel, you simply find the product of the two resistances, then divide by the sum of the two resistances. So it's going to be R is equal to R1, R2 over R1 plus R2. Please let me know in the comments where you need further clarification. So I'm going to end the video here on Kirchhoff's laws and resistances. Signing out.